Welcome to the ChemDoctor, and the purpose of this video is in response to a request I've had on my website to produce more videos that help the viewer with limiting reactants and theoretical yields. Now you can see in this problem that we've been given mass amounts of two reactants, of the only two reactants that are in the reaction, and in this case we're solving for the mass or the theoretical yield of a single product. Now, to practice a limiting reactant problem where you're given masses of reactants, I've chosen to use a chemical reaction that only produces one product. And some of the viewers are going to notice that when I start into the section here where we're going to be solving for the mass of the other reactant used or the mass of the remaining reactant, that you could very easily use the law of conservation of mass to solve this problem. And you'll notice that I'm not going to mention it and that I'm not going to use that ability. Why am I going to do that? It will be because if in a high school chemistry class or an advanced placement chemistry class or even university level general chemistry, usually the professor or the teacher is going to question you about this utilizing chemical equations that have more than one product. And in that case, the ability to use the law of conservation of mass is going to break down, because usually you don't know the mass of the other products, and so you can't use simple subtraction. And I would discourage the viewer from solving these kinds of problems using that method for that very reason, because you don't want to train yourself into something that's not going to happen on the assessments. All right, so let's get into this thing. We're going to be calculating the theoretical yield and mass of the aluminum chloride. We've been given two reactants, mass amounts of both reactants. Remember that your coefficients from the balanced equation are in units of moles. So what complicates this problem, unlike some of the other videos that I've produced in this area, is that the two reactants we've been given are in mass, yet the coefficients of the balanced equation are in moles. So the first step that we're going to have to contend with here will be to convert from the mass of the reactants into moles of reactants. So this problem is going to be solved using the same kind of technique that we used in the simpler versions, except that we have an initial step where we're going to have to convert mass of the aluminum and mass of chlorine into moles. So let's go ahead and get started with this. We're going to create a stack where I'm going to write down the information that I was given. Make sure to not only include the units, but also the labels, so you can clearly see what you're working with here. And in the first step, we need to get both the aluminum and the chlorine into mass. So, or excuse me, into moles. So the viewer is going to need a periodic table, and I would encourage you to pause the video anywhere that you need to in order to do the molar mass calculations that I'm going to be talking about. When you look aluminum up, you're going to find that it's 26.98 grams per mole. The chlorine comes in at 35.45, but remember there are two of them here. And also, remember, do not use the coefficients from the balanced equation to calculate molar mass. So the molar mass of the chlorine is going to be 70.9. Now let's go ahead and use that information. We're going to be solving for moles of both of these, so we're going to need a mole in the numerator of the fraction, or the top of the fraction for both of these. All right, and then what goes in the bottom will be the mass. All right, in the case of the chlorine, we have 70.9 here. All right, now you can see that the grams are going to cancel with the grams of aluminum, and the grams of the chlorine will cancel with the grams of the chlorine. And in both cases, we will have solved for moles of the respective element. So up here we're solving for moles of aluminum, and here we're solving for the moles of the chlorine. All right, so let's see what we get for the aluminum. We're going to have 0.0741. And in the case of the chlorine, we're going to have 0.0282. All right, and remember, you do not want to make a decision concerning limiting reactant at this stage, and the reason is because you've got coefficients in these balanced equations. So actually what you want to do is take this to the next step and actually solve for the product. And then what we're going to do is we're going to compare the amount in moles of the product that we get from both equations, and whichever reactant produced the smaller amount of product, that had to come from the limiting reactant. So again, what we're going to do now is look for another ratio from the balanced equation, or excuse me, we're now looking for the ratio from the balanced equation. And for the top reaction, we're going from aluminum to AlCl3. So we're going to take the 2 that's here, and we need to drop that down into our ratio. So we're going to have 2 AlCl3s here. We're also going to have 2 AlCl3s here. We're solving for the same product in both cases. For the top reaction, all right, we want the aluminum to cancel, so we're going to need to pull down the coefficient for the aluminum, like that. And for the bottom reaction, we need the coefficient from the chlorine, so that's a 3. Now we see that moles of aluminum cancels with moles of aluminum, and we've solved for moles of AlCl3. In the bottom, we've canceled moles of chlorine with moles of chlorine. All right, and we will have solved for moles of AlCl3 like the top reaction. All right, so let's see what we get. In the top one, you see we got 2 over 2, which is 1. So this top equation is going to equal 0.0741 moles of aluminum chloride theoretical yield produced if the other reactant was in excess. And for the bottom one, we're going to get 0.0188 moles of AlCl3 produced. Now, when you compare these two values, you can see that this number here is smaller than this number here. So that makes the chlorine the limiting reactant. I'm going to go ahead and label it as Lr. And the aluminum is the stuff that was in excess. It's the reactant in excess. So the bottom line is here is that the chlorine is going to run out before the aluminum. And once the chlorine runs out, then the reaction stops. And that means that the production of AlCl3 is totally dependent on the limiting reactant. In fact, I'm going to put that in words. Depends on the Lr. Now, since we have figured out that the limiting reactant is the chlorine, then to get to the mole, or to get to the mass or the theoretical yield of the AlCl3, all we need to do is multiply by the molar mass of the aluminum chloride. So to find that, it's going to be 26.98 plus 3 times 35.45, and I get a grand total of 133.33 grams per mole. All right, so coming down here, we're going to multiply by 133.33 grams per mole, put my units in. Moles of AlCl3 cancel the moles of AlCl3, and we get our grammage, which is going to equal about 2.51 grams of AlCl3. And I'll circle this. This is our Theo yield in mass of the product. All right, now, the next thing that we need to do is to solve for the mass of the remaining reactant, because see, this aluminum here is in excess, And that means that not all of this 2 grams is going to be used up. Some of it's going to be left over. So what we're going to do is we're going to calculate first how much of this aluminum was used up in the reaction. And then we're going to use simple subtraction to come back and figure out how much of the aluminum is left over. The key here that you need to understand is that in order to calculate that, you have to use the limiting reactant. So I'm going to pull down the moles of the chlorine again. I'm going to make sure to write the unit and the label. This is my limiting reactant. And then we're going to use the ratio once again from the balanced equation. Only this time we're going to solve for the aluminum. We want to know how much aluminum actually reacted with the chlorine. So we need the 2 from the aluminum here, which we've got. All right, and then we're going to need the 3 from the chlorine down here. Moles of chlorine cancels with moles of chlorine, and we have now solved for moles aluminum. All right, and I'm going to be I'm going to say exactly what this is. Moles of aluminum used up in reaction with the chlorine. So I have it right in front of me. I can see what it is I've solved for. And the value that we're going to get here is going to be 0.0188 moles of aluminum used in the reaction. And I'm going to take this now directly to mass. So we need the molar mass of the aluminum. Moles cancels with the molesies. All right, and what I'm going to get for my mass of aluminum used is going to be 0.507 grams of Al used up, used in reaction. Let me fix that 5 a little bit so it's clearly written. Okay, that's better. Now this is used in the reaction. So now what I'm going to do is I'm going to pull down the mass of the aluminum that was given to us in excess. And I'll label it. We're going to subtract from that the mass used. And what we have left over is going to be 1.4. Whoops. My writing's atrocious. I apologize. It's going to be 1.493 grams. This is approximate. I'm not paying any attention to significant figures. This is the aluminum that is left over or remains after the reaction is over. All right? I'll go ahead and circle that. Okay, now, if you add these guys up, if you take and you add this value and this value, you end up with 4 grams, and that's the amount of material that was originally put into the reaction. So you can tell that this is consistent with the law of conservation of mass. All right? Now, with that, I'm going to go ahead and close the video. I'd like to thank the viewer for watching and coming to ChemDoctor. I'd like to let you know that there are more videos at www.chemdoctor.org. All right? Thanks for coming, and I hope that I see you again.